So hello everyone, welcome to another video on discrete maths. In the last video we talked about this proof technique called induction, and then using this proof technique we prove several theorem. In this video we are going to continue with that topic. We are going to look at a very similar kind of proof technique. This is called strong induction. Alright, strong induction is also called second principle of mathematical induction and is also called complete induction. Alright, so these are some alternative names for this proof technique, that is strong induction. So when we call this proof technique that we are going to learn in this class, when we call this complete induction, the proof technique that we studied in the previous class, that would be called incomplete induction. Okay, now this is a very unfortunate terminology because there is nothing incomplete about what we did in the last class. Okay, it's a very valid proof technique. If you prove any theorem using the induction like we did in last class, it is still a very valid proof. Okay, so if you prove something using induction, it is proven. Okay, there is nothing incomplete about this proof, but still that technique is called incomplete induction when this technique is called complete induction. So just to give you the difference, in last technique, in induction, what did we do? We assumed some base case and then we prove, we prove some base case and then we assume that some inductive hypothesis is true. That is, we proved for one. Okay, that would be our base case, and then we prove, then we assume that for k our theorem is true, and then we prove that if for k it is true, then it is true for k plus 1. So there was this basis step and there was this inductive step. So if we could prove both of these steps, then we would in essence be proving our theorem. Here in strong induction, what we are going to do is, in our inductive step, we are going to assume this theorem to be true from 1 to k. Okay, so we are going to assume that p of 1 is true, p of 2 is true, p of 3 is true, up to p of k is true. Okay, so previously we assumed only p of 1 is true. Here we assume everything from 1 to k to be true, and then we will prove that p of k plus 1 is true. Let me explain this with an example. Okay. So if it seems confusing what I just said, I hope after this example the confusion will go away. Let us say, going back to the analogy, that infinite ladder that we have. So we have some infinite ladder, okay, and there are various steps in this ladder. Okay, so we are given that number 1, we can go to step 1 and 2, and number 2, if we can go to a step, then we can go 2 steps higher. Okay, that means we are given that we can go to step 1 and 2. Okay, and if we go to some step, say x, we can go to step x plus 1. Alright, what did we do in induction? Using our normal induction, we had some base step. Okay, this is also called basis step. Okay, basis step. So don't worry about the terminology, I call it base. So we assumed p of 1, not assume, sorry, we know that p of 1 and p of 2 is true. We can go to step 1, we can go to step 2. Here our proposition p say is this: p of x means we can go to step x. Alright, so our base case would be p of 1 and p of 2. Okay, so we know this to be true. We have proven this. How do we prove this? We know this from our given facts. These are given to us. Alright, so these are proven from our given statement itself. Now our inductive hypothesis, in our normal induction we would have assumed P of K to be true. Okay, and our inductive step would have been, assuming that this is true, we would have proven that if P of K is true, then P of K plus 1 is true. Okay, this is our normal induction. Now what would have happened? Okay, we would somehow have proven this. Okay, if we could prove this, we would have proven that we can go to any steps on this ladder. That is what we are required to prove. We are required to prove, given these facts, that we can go to any steps in this ladder. Okay, in our normal induction we would have proceeded in this manner. Okay, we would have proven our base case, and we have proven our base case. We have proven our base case using the definition itself. Point 1 gives us proof of our base. Okay, then we would have assumed some inductive hypothesis, and then we would have proved this inductive step. But then the problem here is this: there is no way we can prove this inductive step. Okay, if we can go to step K, then our statement 2 tells us that we can go to K plus 2. Okay, so we know if we can go to step K, we can go to step K plus 2, or if we can go to step K minus 1, we can get to step K plus 1. But there is no way to prove that if I can go to step K, I can go to K plus 1. Okay, we don't have information to prove this fact. Now, how do we prove this? How do we prove that we can go to any steps on this ladder? Okay, so what to do? We can use strong induction here. Okay, in our strong induction, now we will try to prove this using strong induction. In our strong induction, we are going to have the same base. Okay, and we are going to have this different inductive hypothesis. We are going to assume that for all j, P of j is true, where j is what? J is from 2 up to k, and k is the last base step or greater than the last base step. Okay, so k is greater than or equal to 2. Okay, this is our inductive hypothesis. See, previously what was our inductive hypothesis? Previously we assumed only for pk. Okay, now what we are assuming? We are assuming that p1 is true, and p of 2 is true, and p of 3 is true, and so on up to P of K minus 1 is true, and P of K is true. Okay, so in our inductive hypothesis we are assuming all of them to be true. Previously we assumed only the base case and this inductive hypothesis to be true, right? We did not assume all this to be true. So P3 up to Pk minus 1 we did not assume to be true. Now we are assuming that all of these are true. Okay, so in our inductive step we have to show that if all of these are true, then P of K plus 1 is true. Okay, previously what did we do? We showed that if P of K is true, then this is true. Now what we are going to do? We are going to show that if all of them are true, then this is true. Okay, so let us try to show this. Okay, what do we know about this thing? K. K is greater than or equal to 2. Okay, and therefore K minus 1 is greater than or equal to 1. Okay, and what do we know about P of K minus 1? We had assumed all of this to be true, so we have assumed P of K minus 1 also to be true. Okay, so we had assumed that P of K minus 1 is true. Okay, we assumed all of this to be true. P of that 1, 2, 3, all of them from 2 up to K. So K minus 1 is less than K. So we assumed that P of K minus 1 is also true. So we had assumed that this is true. Okay, now if this is true, What do we know from point 2? From point 2 we know that if I can go to k minus 1 step, I can go to the step after, means I can go 2 steps higher, right? So k minus 1 plus 2 would be, I can go to step k plus 1. Okay, so I know I can go to k minus 1. This I know because of my inductive hypothesis. Now since I know I can go to k minus 1, I know because of point 2 that I can go to k plus 1. Okay, so what did I do? Under this assumption of my inductive hypothesis, assuming that all of these are true, I have proven that this is true. Okay, so this is how I have proven my inductive step. This is my inductive step. Alright, so this is how, after proving my inductive step, I have proven my theorem. My theorem that I can go to any steps on this ladder. Alright, now this also makes sense, right? I can go to step 1 and I can go to step 2. Since I can go to step 1, I can go to step 2 steps higher, that is step 3. Since I can go to step 2, I can go to step 4. Since I can go to step 3, I can go to step 5. Since I can go to step 4, I can go to step 6. So this is how I know that I can go to any step on this ladder. Alright, so it makes sense. So this is how we have proven that we can go to any step on this infinite ladder. Alright, so this, we saw that it was difficult to prove this theorem using our normal induction that we studied in our last video, but using this new methodology, it is possible to prove this thing. Alright, now let us prove another theorem. If n is an integer, okay, and n is greater than 1, so n is a positive integer greater than 1, okay, then n can be written as a product of primes. So if I take any integer greater than or equal to 2, okay, so greater than 1 means 2, 3, 4, any positive integer that can be written as product of prime. So I can do prime factorization of any integer. Alright, so I have to prove this. Now I will try to prove this with this strong induction. Alright, so I will have a base case, I will have the basis step. So my basis step I am going to prove for 2. Okay, so 2 I know is 2. So 2 can be written as a product of itself, right? So my base case I have proven. Okay, that say my proposition P of x means x is a integer x greater than 0 that can be written as a product of primes. Okay, so I have seen that 2 can be written as a product of prime. So P of 2 I know is true. Okay, we have proven that. Now our inductive hypothesis is going to be this. Inductive hypothesis, I am going to assume that it is true not only for k but also for all numbers from 2 to k. Okay, so for all j, P of j is true. What is j? J goes from 2 up to k. So from 2 to k, I am assuming that all of them are true. Okay, so for all these integers they can be written as product. This is k. Okay, so from 2 to k I am assuming that all these integer 2 up to k can be written as product of prime. So what is k? K has to be greater than or equal to our last base case. So in our case the last base case is 2. So k will be greater than or equal to 2. Alright. So this is our inductive hypothesis. Now given this assumption, I have to prove that P of k plus 1 is true. Okay, given this inductive hypothesis that P of 2, P of 3, P of so on up to k, P of k is true, assuming this, I have to prove that P of k plus 1 is true. Okay, let us go ahead and prove this. Okay, let's see. K plus 1. Now there are two things that k plus 1 can be. Okay, k plus 1 can be prime or k plus 1 can be composite. Alright. So if k plus 1 is prime, okay, then it can be written like 2 was a product of itself, that k plus 1 would be a product of itself, right? So if k plus 1 is a prime, it can be written as a product of prime itself. So for k plus 1, if it is a prime, no need to do anything. Alright. If it is composite, what does this mean? If any number is composite, k plus 1 is composite, that means it can be written as product of two numbers, where both a and b is not equal to 1, b is not equal to 1, and a is not equal to k plus 1, and b is not equal to k plus 1. Okay, so apart from 1 and k plus 1, okay, if k plus 1 is composite, that means it is a product of two different number which is different from 1 and itself. If the only prime factors of some number is 1 and itself, then we know it is a prime number. This is not a prime number, so it must have factors apart from 1 and itself. So we are taking those kind of factors that are not 1 and itself. Okay, so we know there are numbers a and b such that a and b are not 1 and a and b are not k plus 1. So what is a and b? A and b are this. So a will be some number that is between 2 and k. Okay, it is not 1, it is not k plus 1, so it is some number between 2 and k. Similarly, b is some number between 2 and k, same reason, because these are not these are not 1 and itself. Okay, we are not talking about those two factors, 1 and itself. So apart from those, we are taking other numbers which this number will be between 2 and k. Okay, it will be less than k plus 1 and it will be greater than 1. So it will be something between 2 and k. Now what do I know about these two numbers? I know P of A. Okay, let me write over here. I know P of A and P of B, both of these are true. Why do we know this? We know this because this is what we assumed in our inductive hypothesis. In our inductive hypothesis, we assume that P of 2, P of 3 up to P of k is true. Alright, so this A is somewhere between here and here. One of these numbers is A. So P of A we had assumed in our inductive hypothesis to be true. Similarly, P of B is somewhere between here and here, and this is what we assume to be true. So P of B is true. So we know P of A is true and P of B is true. What does that mean? That means that this A can be written as a product of primes. So there will be some prime numbers whose product will give me A. Similarly, there will be some prime numbers whose product will give me B. Say X, Y, Z are prime numbers whose product gives me A, and P, Q are prime numbers whose product gives me B. Okay, so what is this? If I multiply those two, all of these are prime numbers, right? This gave me A, this gave me B. I know this A has some product of primes, I know it from here. B has some product of prime, I know it from here. B can be written as product of prime. So this is said a product of prime for A, this is product of prime for B. These are all prime numbers, so this is a product of prime. Okay, I have multiplied these two. So all these are prime numbers, and this product of prime is equal to k plus 1. Right? So we know p of k plus 1. Okay, in case of composite number p of k plus 1, we have shown that this k plus 1 can also be written as a product of primes. So p of k plus 1, that is k plus 1, can be written as a product of prime. This statement is true. Okay, so previously we had shown that in case k plus 1 is a prime, it is true trivially, and in case it is not a prime composite, we have shown by proving, by doing all this, that k plus 1 can be written as a prime. So we have shown anyway that given our inductive hypothesis, okay, given our inductive hypothesis was that all this p of 2 up to p of k, given all of these are true, we have shown that p of k plus 1 is true. Okay, so assuming that from 2 to k, if all of this can be written as product of prime, then under this assumption k plus 1 can be written as a product of prime. So this completes our proof. Alright, I hope you understood this. Let us now prove another thing. Okay, so this was a very simple proof, right? If you did not understand, I suggest that you go back and watch this video again. Okay, now let us try to prove something. You know what is a postage stamp? I hope you know what is a postage stamp. You post something somewhere, so you have to buy this stamp from post office. You fix this post stamp on top of some envelope, okay, and then you post this envelope, okay, carrying your letter. So this postage stamp maybe to send somewhere, you need say 20 rupees worth of stamp. Okay, so if you need 20 rupees worth of stamp, you will buy, say, only 4 rupees and 5 rupees stamps are available. So what will you do? You will buy, say, 5 different, so you need 20 rupees worth of stamp, only 4 rupees and 5 rupees stamps are available in the post office. So what can you do? You can buy 5 4 rupees stamp, or you can buy 4 5 rupees stamp and stick them together. So if you stick 4 5 rupees stamp, that is also 20 rupees worth of stamp. Alright, so I hope you have posted stamps before, posted letters through post office, so I hope you understand what I am talking about. So given that, here is the theorem. Any postage stamp above or equal to rupees 12 can be composed with rupees 4 and rupees 5 stamps, postage stamps. So what is the claim according to this theorem? The theorem claims that any value of stamp you need, okay, above rupees 12, so you need 12 rupees worth of stamp, 13, 14, anything, okay, up to infinity. So any amount of postage stamp you want, if you have access to rupees 4 and rupees 5 stamps, okay, these are the only 2 stamps available in the post office, say, then you can make any amount of stamp necessary using only this 4 rupees and 5 rupees worth of stamp. Okay, so this is the theorem. Let us go ahead and prove this. We will first prove it using normal induction, then we will see how strong induction makes this proof easier. Okay, so let us prove using normal induction. In our normal induction, we will have this base case, right? So base case is what? Base case is say our proposition that we are trying to prove is this: P of x, rupees x worth of postage stamp can be made with rupees 4 and rupees 5 postage stamp only. Okay, so only rupees 4 and rupees 5 worth of postage stamp is necessary. We don't need any 2 rupees, 3 rupees postage stamp. We don't need any 6 rupees, 7 rupees, anything. Only 4 rupees and 5 rupees is sufficient. So say to make 12 rupees worth of postage stamp, I can take 4 rupees worth of postage stamp. I don't use any 5 rupees. That is not a problem. It is not necessary that I have to use both. Okay, but then what is necessary is that apart from these two, I don't use any other. Okay, so 12 rupees and anything above 12 rupees. That is the set that we are talking about. Okay, we are not talking about say 4 rupees worth, 3 rupees worth of postage stamp. Of course, we cannot make 3 rupees worth of postage stamp using only 4 rupees and 5 rupees. Alright. Similarly, we cannot make say 7 rupees worth of postage stamp using only 4 rupees and 5 rupees. Okay, so we are talking about 12 and more than 12. So, yeah, is our base case. What is our base case? Base case, what is the smallest value in our set? That we will consider the base. 12 is the smallest. So we are talking about 12, 13, 14, 15. 12 is our starting point. So let us see if we can prove for our base case. Okay. So 12, if we take 3, 4 rupees worth of stamp, okay, that will give us 12 rupees worth of stamp. So yeah, 12 rupees worth of stamp can be made with 4 rupees and 5 rupees. We have proven this. Now our inductive hypothesis, we are going to assume that it is true for P of k. In our inductive step, we have to prove this inductive step that for if P of k is true, then P of k plus 1 is true. Okay. Now before we prove this, there are two cases possible. Alright. Case 1 is rupees k postage stamp is made with one or more rupees 4 postage stamp. Okay, so there are two cases possible. In one case, rupees 4 worth of postage stamp was used. Okay, in the other case, rupees 4 postage stamp not used. Okay, so say I am trying to make postage stamp worth rupees 15. I can use 3 5 rupees postage stamp. So 4 rupees worth of postage stamp was not used. Okay, so my k is of course bigger than 12. We are talking about numbers equal to or above 12. So that is what we have. Okay, k is greater than or equal to 12 in our case. So let us see if we can prove for these two cases. Okay, so case 1 is what? Case 1 is a 4 rupees postage stamp was used to create k rupees worth of postage stamp. So we use several postage stamp plus at least one postage stamp, and this gave us k rupees worth of postage stamp, right? So there were a few postage stamp over here. Okay, so since it is bigger than or equal to 12, so definitely apart from this 4, some other postage stamp was also here. So this may be 5 rupees and 4 rupees worth of postage stamp, maybe several of 4 rupees, several 5 rupees, we don't care what is here. Okay, some postage stamp, and we know only 4 rupees and 5 rupees postage stamp were here. Okay, and then at least one 4 rupees postage stamp was used. So this plus this was equal to k. Okay, now what we are going to do? We are going to remove this 4 rupees worth of postage stamp. We know at least one of them was used. We are going to remove them. All of them will stay the same. I will add a 5 rupees postage stamp in its place. Okay, I will remove this 4 rupees worth of postage stamp and I will add this 5 rupees worth of postage stamp. So here was k minus 4 rupees worth of postage stamp. Okay, so k minus 4 plus 1 4 rupees worth of postage stamp gave me k rupees worth of postage stamp. This k minus 4 was also made with 4 rupees and 5 rupees postage stamp. Okay, this k minus 4 I will keep as it was. All this 4 rupees and 5 rupees postage stamp, they will be the same. This one postage stamp that was worth 4 rupees, I will remove that and I will put a 5 rupees postage stamp in place of this 4 rupees postage stamp. So what is the amount of postage stamp I have now? I have k plus 1 rupees worth of postage stamp. Okay, so under our inductive hypothesis assumption that I can make k rupees worth of postage stamp using this 4 rupees and 5 rupees, I have proven that I can make k plus 1 rupees worth of postage stamp. So for case 1 I have proven this. Now for case 2. Case 2, only 5 rupees worth of postage stamp was used. Okay, now there is this observation I want you to make. What is the minimum value? Minimum value was 12. Alright, so I used only 5 rupees worth of postage stamp. How many postage stamp can I use? If I use 2, then I will get a sum equal to 10. Okay, so that is less than 12. I know my value of k, the amount of postage stamp that I am making is greater than 12. So I will need at least 3. Okay, otherwise it will be less than 12. So if I use 3, it can be 15. If I use 4, it will be 20, and so on, right? But I will need at least 3, because if I use 2 5 rupees worth of postage stamp, it will give me it will give me 10, which is less than 12. So I have to, my total value, my k is greater than or equal to 12, so I will need at least 3. Okay, and I am not using, in my second case, I am not using any 4 rupees worth of postage stamp. So what will I have? I will have minimum 3 5 rupees worth of postage stamp. Okay, and apart from this I will have 0 or more than 0 worth of postage stamp. Okay, so this is k minus 15 worth of postage stamp plus 5 plus 5 plus 5, together they are giving me k rupees worth of postage stamp. Okay, so under my assumption I know for k rupees worth of postage stamp I can make using 4 rupees and 5 rupees. If I use 4 rupees worth of postage stamp, that case I solved. Now I am not using 4 rupees, this case I am going to solve. What am I going to do? I know I have minimum 3 5 rupees worth of postage stamp. I will remove this 3. Okay, so I will remove this 3 5 rupees worth of postage stamp, and instead I will use 4 rupees worth of postage stamp. Alright, now this k minus 15, apart from this 3, the other 5 rupees worth of postage stamp, I may have 0 or more than 0 other stamps. Okay, that I will keep as same as it was before. This k minus 15, this I will keep as it was before, but I will remove this 3, and in its place I will put 4 rupees worth of postage stamp. Now this is equal to how much? This is equal to k plus 1. Okay, so k minus, I remove 15, 5 rupees, and added 16, 4 rupees. So k minus 15 plus 16 is equal to k plus 1. So what did I do? Previously I had k rupees worth of postage stamp which was made only with 5 rupees. Okay, so now I have k plus 1 worth of postage stamp. This is made with only 5 rupees and 4 rupees. Okay, so k plus 1 I can make only with 4 rupees and 5 rupees worth of stamp. So this is how I have proven for my case 2 also, where previously 4 rupees stamp was not used. Now what did I prove? I proved that if I can make k rupees worth of postage stamp, okay, then I can make k plus 1 rupees worth of postage stamp using only 4 rupees and 5 rupees worth of postage stamp. Alright, so this is how I have proven my inductive step, and by proving my inductive step I have proven my theorem. Now this proof was using the normal induction that we did in our last class. Okay, let us now do this proof again, and this time we are going to use strong induction. Okay, so you can see we had to bring it down to cases, and then we had to solve using different cases, right? Using normal induction, we will see if we can simplify it using strong induction. Okay, so in our strong induction we will have more than one base, we will have different bases. Okay, so P of 12, I know it is true, I can make with 4 rupees worth of postage stamp. What about P of 13? P of 13 I can make with 2 4 rupees and 1 5 rupees, right? 8 plus 5 is equal to 13. Then P of 14 I can make with 1 4 rupees and 2 5 rupees, right? And P of 15 I know it's true because I can make with 15 rupees worth of postage stamp, I can make with 3 5 rupees worth of postage stamp. Okay, so I know in my base case what did I do? I assumed all of this to be true. No, sorry, I did not assume, I proved all of this to be true. That P of 12, 13, 14, 15. Okay, so 12 rupees, 13 rupees, 14 and 15 rupees worth of postage stamp can be made only with 4 rupees and 5 rupees worth of postage stamp. This is my base case. I had 4 different predicates that I proved in my base case. Alright, next is my inductive hypothesis. In my inductive hypothesis, I am going to assume that for all j, P of j is true. So what are the restrictions on j? J is from 12, okay, from the start of my base case up to what? I will assume everything to be true up to k. So j will be true up to k, and what is k? K will be equal to or larger than my last base case. Last base case is 15. So k will be larger or equal to 15. Okay, this is my inductive hypothesis. What is my inductive hypothesis? I have assumed that P of 12 is true, and P of 13 is true, P of 14 is true, P of 15 is true, and so on up to P of k is true. Okay, this is my inductive hypothesis. I have assumed this. Okay, now under this assumption of my inductive hypothesis, I have to prove my inductive step. My inductive step is this, that under this assumption, given it that all of these are true, P of k plus 1 is true. Okay, now let us go ahead and prove this. Okay, so let us talk about P of k minus 3. What do we know about k minus 3? I know k is greater than or equal to 3. What was k greater than or equal to? K was greater than or equal to 15. Okay, the last of my base case. Now if I subtract 3 from both sides, I will get k minus 3 is greater than or equal to 12. Okay, now what do I know? I know that P of 12 is true. Okay, P of 13 is true, so on. What do I know about P of 3? P of 3 I had assumed up to P of k is true. Okay, I had assumed P of 12 is true up to P of k is true. Okay, all of this in between I assume to be true. Now what do I know about k minus 3? I know k minus 3 is this or greater than this. Okay, that is what is written here. I know k minus 3 is 12 or greater than 12, and I know k minus 3 is less than k. Okay, definitely less than k, 3 steps before k, but is greater than 12 after this. So is equal to this or after this. So I know it is somewhere in here. Okay, now all of this I assume to be true, that all of this can be made with only 4 rupees and 5 rupees stamp. All this value 12, 13, 14, 15 up to k. Okay, so I know k minus 3 can also be made with 4 rupees and 5 rupees stamp. So I know this is true. Okay, that P of k minus 3, that k minus 3 worth of postage stamp can be made only with 4 rupees and 5 rupees worth of stamp. I know this is true. Okay, so P of k minus 3 is true. That is k minus 3 rupees worth of postage stamp can be made with only 4 rupees and 5 rupees worth of postage stamp. Now what will I do? I will add another 4 rupees worth of postage stamp. Okay, k minus 3 I was able to make with 4 rupees and 5 rupees. Now k minus 3 I am making with 4 rupees and 5 rupees. Okay, and then I buy another 4 rupees worth of postage stamp and I put next to this k minus 3. What is the total that I have now? Now k minus 3 I had previously, I am adding one more 4 rupees postage stamp. So my total value now is k plus 1. So what did I do? I made k plus 1 worth of postage stamp using only 3 4 rupees and 5 rupees worth of postage stamp. Okay, so that is how I have proven that P of k plus 1 is true. Okay, so I have proven this. How did I prove this? I proved this under my assumption that P of 12 and so on up to P of k is true. P of 12, 13, 14, 15 up to k is true. Okay, under this assumption I have proven that P of k plus 1 is true. So I have proven my inductive step, and by proving this inductive step and by proving my base case, I have proven that this is true. Okay, now this proof is if you get it, okay, if you get what is strong induction, you will see that this proof is easier than the proof that we did previously using normal induction. Okay, so one more reason why you might prefer strong induction even in places where normal induction can do the proof. Okay, now one more thing I want to tell you, this is a very important technique. Okay, you have seen proofs we have done with strong induction that we cannot do with normal induction. Okay, you will get this strong induction, you will require this strong induction in graph theory, in finite automata, all these subjects. So understand this proof technique as well. Okay, this is important. So we have done 2 or 3 proofs. All right, now let us look at something called recursively defined function. So you are in computer science, you have studied programming back in first year itself, now you are in 4th sem. So by now you know what is recursion. Okay, at least in programming language you know what is recursion. So I will not go ahead and explain this to you in very much depth, but let us look at recursion. Okay, let me explain recursion with one example. So factorial of some number n. How do we find factorial of n? Okay, very easy. Factorial of 4 is equal to 4 into factorial of 3. Correct? 4 factorial is equal to 4 into 3 factorial. This is correct, we know. Alright. So we can write this factorial, this program to find factorial. Okay, it will return n into factorial of n minus 1. Okay, so this is a recursive function. Now what will happen if I say call factorial of 3? What will it return? It will return 3 into factorial of 2. Then it will try to find factorial of 2. What is factorial of 2? Factorial of 2 is equal to 2 into factorial of 1. What is factorial of 1? Factorial of 1 is 1 into factorial of 0. What is factorial of 0? Factorial of 0 is 0 into factorial of minus 1. What is factorial of minus 1? It will return minus 1 into factorial of minus 2, and so on. It will go into an infinite loop. Okay, we don't want it to go into infinite loop, and moreover factorial of minus 1, factorial of minus 2 does not make sense. These are not defined. Okay, so what do? We have to stop this recursive call somewhere, right? So where will we stop? We know that the first value that has a factorial definition is 0. We know 0 factorial is equal to 1, so we will stop at factorial of 0. Okay, so we will give a condition check in here. If n is equal to 0, then return 1. Okay, now if we call this function factorial of 3, it will work properly. So factorial of 3 will do what? 3 into factorial of 2. Factorial of 2 will do what? 2 into factorial of 1. Factorial of 1 will do what? 1 into factorial of 0. Factorial of 0 will come here, will return 1. Okay, then factorial of 1 will get back this factorial of 0 equal to 1. So it will do 1 into 1 and it will return. So factorial of 2 will get back 1 into 1 equal to 1. So it will do 2 into 1 and it will return 2. So factorial of 3 will get 3 into factorial of 2, that was 2. Factorial of 2 returned 2. So factorial of 3 will return 3 into 2 equal to 6. Okay, so 6 is the correct value for factorial of 3 and that will be returned by our function. Okay, so what do we have in here? We have two different things in here. We have this thing and we have this thing. This is called the basis step. Okay, or base, and this is called the recursive step. Alright, this is the basis step, this is the recursive step. Now when we write a function in this manner using a basis step and a recursive step, that kind of function is called a recursion or a inductive definition. Alright, so we have this factorial. Okay, this is in programming language notation. We will no longer see this kind of notation anymore in this course. Okay, this is something that I wrote in order to explain to you. Okay, the same thing in this our new notation would have been, say f is our function, then f of 0 would have been 1, f of n plus 1 would have been, or f of n, say, okay, let me write n plus 1, does not matter, will be n plus 1 into f of n. Okay, this notation is similar to what we wrote in our programming language notation. Okay, this is the basis step, base, this is the recursive step. Okay, now let me give you an example. Say my basis is 3 and my f of n is equal to 2 into f of n plus 1 is equal to 2 into f of n plus 3. Okay, so this is the question that I have. This is the definition that I have. My question is find f of 4. Okay, so this is what we are going to find here. Alright, now to find f of 4, what will I do? I will go to this recursive step, recursive definition. Alright, it will be 2 into f of 3 plus 3. What is f of 3? F of 3 is again 2 into f of 2 plus 3. What is f of 2? F of 2 is 2 into f of 1 plus 3. What is f of 1? F of 1 is 2 into f of 0 plus 3. What is f of 0? F of 0 is 3. Okay. Now we have done finding this. We will go back and substitute. Okay, we will substitute f of 0 first. What is f of 0? F of 0 is equal to 3. So f of 1 evaluates to 2 into 3 plus 3. This is 6 plus 3 equal to 9. So f of 1 is equal to 9. Now we will substitute f of 1 in the previous equation. F of 1 is 9. So 2 into 9 is 18 plus 3 is equal to 21. Okay, so this is 21. We will substitute f of 2 equal to 21. 21 into 2 is 42 plus 3. This is equal to f of 3 is equal to 45. Okay. Now we will substitute 45 in here. Okay. So 2 into 45 plus 3. This is equal to 93. Okay. So this is how I know my f of 4 is equal to 93. So this is how I have found f of 4. Okay. Okay, I should not have either than this. Okay, but I can erase this. Okay, let us see. Let us do one more example. Okay, I want to write this definition of a to the power n. Okay, where a is not equal, a is a integer, and a is not equal to 0, and n is non-negative integer. Okay, so a to the power n. How do I recursively write this thing? Okay, my basis step will be a to the power 0 is equal to 1. Okay, so this is obviously true. If a is not equal to 0, then anything to the power 0 is equal to 1. Okay, we are talking about integer. Sorry, no need to do integer. We can do it for a is equal to real number. Okay, so a is some real number not equal to 0. Any real number to the power 0 is equal to 1. Okay, now what is our inductive step? A to the power n plus, what is our recursive step? A to the power n plus 1 is equal to a into a to the power n. Okay, so these two lines, this basis step and this recursive step, this is enough to define this. Okay, using these two steps we can calculate the value of this. Alright, so yeah, this is what we have. So this is another example of recursive function. Okay, now let us talk about another, let me talk to you about a series. Okay, this was made famous, this had been famous from far long, but I learned about this when I read this book called Da Vinci Code by Dan Brown back in high secondary. When I was in class 11, I read this book. Okay, so this movie was coming out and I used to like Tom Hanks, I still do. So before the movie released, I read this book and I really loved the book. Okay, in that book I learned this series, about this series. It is called Fibonacci series. So when I went to engineering later on after 12, when I read about Fibonacci series, when I was asked to write a program during my first year, C, I was learning about C. Okay, so when I was asked to write a program to print Fibonacci series, I got very excited because I had read about this in this book that I really liked. Okay, anyway, Fibonacci series is this. You have 1, 1, then the next term will be the sum of the previous two terms. Okay, so the next term would be 2, the next term 2 plus 1 is equal to 3, then the next term would be 3 plus 2 equal to 5, next term would be 8, then 13, 21, so on. Okay, now this is f of 1, first Fibonacci term, term 2, term 3, term 4, term 5, term 6. Okay, in some book 0 is written as f of 0. Okay, so this is something we are going to add. So the 0th term in Fibonacci series is 0, the first term is 1, so 1 plus 0 is equal to 1, 1 plus 1 is 2, 2 plus 1 is 3, and so on. This is Fibonacci series. Alright, Fibonacci series we can write as a recursive function, right? So basis I will write later on. Let me write recursive step first. Recursive step would be f of n plus 1 is equal to f of n plus f of n minus 1. Okay, so what will be the basis step? So f of 3 is f of 2 plus f of 1. Okay, f of 2 is f of 1 plus f of 0. F of 1 is f of 0 plus f of minus 1. There is no f of minus 1. So f of 1 will be one of my bases. Okay, another basis is f of 1 I will define in my basis. F of 1 is equal to 1. Now in order to calculate f of 2, I will need f of 1 and f of 0. Since I cannot derive f of 1 using this recursive step, it is in my basis, f of 2 will require f of 0, f of 0 also I cannot use using recursive step. So f of 0 also I need to define in my basis. So unlike the previous two examples, here my basis will have two different conditions, my basis step. Okay, and then my recursive step will give me all of this. Fine. So this is Fibonacci series. Alright, so I hope you can write a program to print the kth term of a Fibonacci series. Now, when talking about Fibonacci series, I want to tell you this basis and recursive. One thing I want to tell you, you can of course write a recursive function to call Fibonacci series. Okay, I want you to do one thing. You can also write this Fibonacci series using an array. Okay, without using this recursion, you can write using an array. What will you do? You will create an array. Okay, you will write the first element as 0, second element as 1. These two you will write manually. This element is onwards you will fill by adding the previous two elements. Okay, so this will be a for loop and you will go on continuing with this for loop. Okay, so try to find fill the try to print the first 100 Fibonacci elements using this method. Write one program and write another program to print the first 100 elements using this method, and do one thing using this time calculation function. Okay, try to figure out how much time these two different programs using these two different methods, how much time are they taking. Okay, you will see that this recursive method is going to take far longer. Okay, and this is true in case of finding factorials also. You can see that in case of factorials, finding factorial, you will see that recursion is going to take longer than using a normal method, just multiplying under a for loop. Why? Because in order to do recursion, you will have to call this function. This calling of function will need the processor to go into do several maintenance tasks. Alright, there will be in our laptop, in our x86 x86 64, there are resistors like base resistor, stack resistor, all of these things. So this has to be shifted to the stack, and then the value has to be shifted in order for your new function to be called. So lot of internal management has to be done. Okay, in case of recursion, when you call a function, so if you keep calling a function over and over again, lots of maintenance has to be done. Okay, so this, in case of factorial, you will see that calling this for loop, using for loop, multiplication under a for loop, is going to perform faster than doing this recursive call. Okay, that you are going to see. In Fibonacci series, this is going to further degrade. Why? See, what are you going to do? You will see that in order to find f of say 4, okay, in order to find f of 4, you have to find f of 3 and f of 2. Okay, in order to find f of 3, you will have to find f of 2 and f of 1. Okay, f of 2 you will find f of 1 and f of 0. These two will come from the base, this will come from the base. But I want you to see one thing. This f of 2 you are calculating here, this f of 2 you are going to calculate again. Okay, similarly, if you are trying to find f of 5, then you will find f of 4 and you will find f of 3. Okay, to find f of 5, you can see that f of 3 is being repeated. You are finding f of 3 2 times, and to find f of 3 you will find f of 2, f of 1. So you can see you are finding f of 2 3 times. Okay, f of 3 2 times. So to find f of 2 using this recursive call, you will be calling again and again. Okay, so this is going to hamper your performance very much. Compare that to this other method that I said, use an array. You will not have this problem when you are using an array. Okay, so these sub problems that you are going to repeated sub problems, if you can memorize this beforehand like you did using an array, okay, that kind of programming paradigm, that kind of algorithm is called a dynamic programming algorithm. Okay, you will see that this exponential kind of things that needs exponential amount of time can be done using a much smaller amount of time. Okay, so this is some extra topic that I am talking about. This is far beyond your not far beyond your course, but this is not necessary in your course right now. Okay, but if see this example, you can see that recursion has some problem. Okay, that is what my point was. You are understanding, I am explaining what is recursively defined function and all these things. These are very powerful tool that you need to know. Okay, there are places where recursion have to be used, all right, but then if possible avoid recursion, because there are disadvantages that comes with recursion. There are two disadvantages that I showed you. One is this, in case of Fibonacci numbers itself. Another is in case of finding factorial, this management has to be done, that can be avoided if not using recursion. Anyway, these are disadvantages of recursion. This should not have been told in a discrete maths. From our perspective of discrete maths, we are not worried about this kind of thing. These are things that you should know, that you should talk about in courses like algorithm. Alright, and you will probably learn discrete maths when you study algorithm later on. You will learn dynamic programming and you will see all this problem when you will learn algorithm later on. Alright, so this is Fibonacci series. Alright. Now, before I proceed, I want to talk about a quadratic equation. Okay, so a little bit of digression again. This is a quadratic equation, right? So you know what is a quadratic equation? A quadratic equation is an equation of this form: ax squared plus bx plus c equal to 0. Okay, so over here, what is a? A is equal to 1, b is equal to -1, and c is equal to -1. So what are the solution to this quadratic equation? I know one of the solution is minus b plus b square minus 4ac by 2a. Another solution is minus b minus b square minus 4ac by 2a. Okay, so this is minus 1 equal to 1 plus root over b square is minus 1 square is 1 minus 4ac. A is 1, c is -1, so minus into -1 is minus 4 into -1 is plus 4, so 1 plus 4 is equal to 5, so it is root 5 by 2a. A is equal to 1, so 2 into 1 is equal to 2. So this is one of the roots of this equation. This is another root. This will be 1 minus root 5 by 2. Okay, so let us ignore this. Let us talk about this. I know this is one of the roots of the equation. Okay, so let me call this phi. Phi is equal to what? Let me rewrite it in here. I have just found that phi is equal to 1 plus root 5 by 2. Okay, so what do I know? I know since x, one of the solution of this quadratic equation is x is equal to phi, that is 1 plus root 5 by 2. So I know phi square minus phi minus 1 is equal to 0. That means phi square is equal to phi plus 1. Okay, now this is a very special number. This is not some random number. Phi is called the golden ratio. Okay, so you will see the use of this golden ratio in many places like design, like photography, okay, and in nature also. Look up golden ratio. Okay, this is a very interesting number. This is something 1.6 something. Okay, this is the irrational number, so there is no end, 1.6 and so on. Okay, this is called the golden ratio, denoted by phi. Very interesting number. Look up in Google what is golden ratio. You will find this golden ratio in design, in photography, in flowers, in nature, cyclone, in the shape of our Milky Way many galaxies. Alright, so there are lots of places in nature where you can see this golden ratio, this phi in action. Okay, that is also not part of our course. What is part of our course is this, that there is this number phi, okay, that is equal to this, and then we have seen, okay, that phi is a solution to this quadratic equation. So this is one of the roots, okay, of this quadratic equation, one of the solution. So I know I can put phi in here. So phi square minus phi minus 1 is equal to 0. I have shifted these two to the right, so I know phi square is equal to phi plus 1. Okay, so these are things that I know. Okay, let me just write down a few points in here that I know. I know phi is equal to 1 plus root 5 by 2, and I know phi square is equal to phi plus 1. Okay, so these are two things that I know. Now here is a theorem. If n is greater than or equal to 3, then f of n, the nth Fibonacci number, is greater than phi n minus 2. Okay, so here is a theorem. We are going to prove this theorem using strong induction. Alright, so n is of course this number greater than or equal to 3, so this is integer. Okay, there is the third Fibonacci number, there is fourth Fibonacci number, fifth Fibonacci number, there is no 3.5 Fibonacci number. Okay, this is an integer and this is greater than or equal to 3. We are going to prove this theorem using strong induction. So we are going to need some basis step. So the minimum step that I can take is 3. We are talking about third and more than third number. So f of 3 is what? Okay, well, before I proceed any further, let me give the proposition. P of 3 means, sorry, P of x means this. X Fibonacci number is greater than 5 to the power x minus 2. Okay, so P of 3, let us verify this. Let us prove this basis step. So it should mean f of 3 is greater than 5. 3 minus 2. 3 minus 2 is 1. So 5. So let us recall f of 1, f of 2, f of 3, f of 4. F of 1 is 1. F of 2 is 1. F of 0 was 0. F of 3 is 2. F of 4 is 3. Okay, and so on. F of 5 is 5. Okay, so f of 3 is 2 and f of 3 is 2. Okay, so this phi, if you can calculate, look up what is golden ratio. Okay, or use a calculator to figure this out. This is 1.6 something. Okay, so using your calculator you can see f of 3 is equal to what? F of 3 is equal to 2 and 2 is greater than 1.6. So we know this is true. Okay, f of 4, is it greater than 5? 4 minus 2. 4 minus 2 is 2. So f of 4, is it greater than 5 square? Once again you can use your calculator to verify this. Okay, you will see that f of 4 is equal to 3, our fourth Fibonacci number. So you can see that 1.6 golden ratio, but that irrational number square is less than 3. Okay, it is 2 point something something. Okay, so I can see f of 4 is greater than 5 square, f of 3 is greater than 5. So p of 3, that is f of 3, the third Fibonacci number is greater than 3 minus 2, that is 5 to the power 1, that is 5. So this is true, we have proven. F of 4, the fourth Fibonacci number is greater than 4 minus 2 square, 5 square, that is also true. By calculation, by using a calculator or by doing calculation, okay, we can figure this out. So we know these two are true. Okay, so this is our base step. We have proven these two are true. Now we are going to do this assumption that for all j, p of j is true. J goes from what? J starts from our base case up to what? Up to k. Okay, and what is k? K is greater than or equal to the last of the base case, that is 4. Okay, this is our inductive hypothesis. Now under this inductive hypothesis we have to prove that p of k plus 1 is true. That is, our k plus 1th Fibonacci number is less than this k plus 1 minus 2. So we have to prove this. To prove, what do we have to prove? We have to prove that k plus 1 Fibonacci number is greater than this 5 square, golden ratio square, k plus 1 minus 2, that is k minus 1. Okay, this is what we need to prove. Alright. So let us try to prove this. Okay, can I do one thing? I should okay, no need. Okay, so this value, let us try to see what this value is. This is k minus 1. This is equal to 5 square into 5 k minus 3 to the power k minus 3. Okay, so this is equal to what? This is equal to this, right? We have done this proof previously. We have not done this proof. We have solved this algebraically, that this is equal to this. So we are substituting that and we are keeping this the same. So this is equal to 5 into 5 k minus 3 plus 1 into 5 k minus 3. So this is equal to 5 into k minus 2 plus 5 to the power k minus 2 plus 5 to the power k minus 3. Alright, so this is something that we have seen. Okay, next is what? Okay, what was our inductive hypothesis? According to our inductive hypothesis, we know that f of k minus 1, okay, is greater than this k minus 1 minus 1, that is k minus 2, and f of k minus 2 is greater than 5 k minus 2, okay, k minus, okay, sorry, I made a mistake. F of k is greater than f of k is greater than 5 k minus 2, okay, and f of k minus 1 is greater than 5 k minus 3, okay. This we know from our inductive hypothesis. Alright, we had assumed that f of we started from our base case from 3, so we had assumed f of 3 is greater than 5 to the power 3 minus 1, f of 4 is greater than 5 to the power 4 minus 1. We had assumed up to k. So we had assumed that f of k is greater than 5 to the power k minus 2, and before k there was f of k minus 1, which is greater than 5 to the power k minus 3. Okay, so this we know is true from our assumption of the inductive hypothesis. Okay, so this is the statement p of k, this is the statement p of k minus 1. Okay, so k is greater than 4, so p of k minus 1 is greater than, k is greater than or equal to 4, p of k minus 1 is greater than or equal to 3. So from 3 up to k we had assumed to be true, right? So this is true, this is true, we know for sure. Alright, now we know 5 to the power k minus 1 is equal to this. We have done this arithmetic algebra and we have found this. Okay, now what do I know? I know f of k plus f of k minus 1 is greater than 5 of k minus 2 plus 5 to the power k minus 2 plus 5 to the power k minus 3. Alright, so this is greater than this is greater than this, so this plus this would be greater than this plus this. Okay, this is basic inequality. Okay, this is greater than this is greater than this, so this plus this will be greater than this plus this. That is what I have written here. Now from the definition of this recursive definition of Fibonacci series, I know this plus this is equal to my k plus 1 Fibonacci term. Kth Fibonacci term plus k minus 1 Fibonacci term will give me k plus 1 Fibonacci term. This is from the definition of Fibonacci numbers. Alright, and then I have seen this plus this is equal to this. So this plus this is equal to 5 to the power k minus 1. Okay, so this plus this is equal to this plus this is equal to this. So this is how I have proven this thing, and this was what was required to be proven by me. Alright, so with this I have proven this theorem. Alright, so lots of steps I have taken. I had proven first for my first base case 3, and then I had proven for 4, and then I assumed this inductive hypothesis 3, 4 up to k is true. Now under my assumption I had this 2 I had assumed to be true. So assuming this true, I have proven that this is true. Okay, so assuming my inductive hypothesis, I have proven that whatever is required to be proven is true. That the nth Fibonacci number, where n is something bigger than or equal to 3, n is an integer, is greater than the golden ratio to the power n minus 2. Alright, so this concludes our proof of the theorem. Okay. Okay, now we are going to go somewhere very different and talk about something else. Alright, we are going to look at something called the Euclidean algorithm. Okay, before we do that, let me talk about GCD. Okay, greatest common divisor. The GCD of two integers. Okay, I have written numbers, so it will be integers. The GCD of two integers is the greatest integer that divides both of them. Okay. So let us try to find the GCD of two number. Okay. So what is GCD? So we have two number. The greatest number that divides both of them will be their GCD. Okay. So let us say I have two number 24 and 36. So 24 is divisible by 1, divisible by 2, divisible by 3, divisible by 4. Is not divisible by 5, divisible by 6, not by 7. It is divisible by 8. Then divisible, not divisible by 9, 10, 11. It is divisible by 12. Okay. Then it is divisible by 24 itself. So these are all the number that divides 24. Alright. Similarly 36, all the numbers that divide 36 are 1, 2, 3, 4, 6. Then 8 does not divide, 9 divides, 10, 11, 12 divides. Okay. 13, 14. Okay, 18 divides 36 and 36 divides 36. We can see that 1 divides both of them. So 1 is a common divisor. 2 divides both of them. 2 is a common divisor. Similarly 3 divides both of them. 4 divides both of them and 6 divides both of them. So all this number 1, 2, 3, 4, 5, 6, all of them divides both of them. So all of these are common divisors of 24 and 36, but they are not the greatest common divisor. The greatest common divisor is 12. Okay, 12 also divides both of them, and among all the numbers that divides both of them, 12 is the greatest. Alright, so because of that reason 12 is their greatest common divisor, GCD. Okay. Now there is one technique we learned this back in school of finding GCD. What we will do, we will prime factorize this number. We will factorize this number into their prime factors. Okay, so let us do it. 24 is equal to 2 into 2 into 2 into 3, right? 2 into 3 is 6, 6 into 2 is 12, 12 into 2 is 24. Similarly 36 is equal to 2 into 2 into 3 into 3. So 3 into 3 is 9, 9 into 2 is 18, 18 into 2 is 36. So these are the prime factorization of 24 and 36. So I will now take common. Okay, what will I do? This 2 I will take as common, this I will take as common, and this 3 I will take as common. So I had taken 2 into I had taken 2 into I had taken 3. So 2 into 2 into 3 is equal to 12. So 12 is their GCD. Okay, so this is one algorithm to find GCD by factorizing the number into its prime factors and then finding finding the common and multiplying the common. Okay, now there is a problem with this algorithm. The problem is that finding prime factor is a very expensive process. It is going to take lots of time. Okay, so because of that reason, this is not a good algorithm. This is in terms of time complexity, this is very expensive. Okay, so is there any better algorithm? That is the question. So before we figure out the algorithm, let us look at some pattern. Okay. Hold on. Say I want to find the GCD of two numbers. Okay. 287 and 91. So I am going to find GCD of two numbers 287 and 91. Let us make some observation. 287, if I divide by 91, I will get 3 as quotient and 14 as remainder. Okay, so 287 divided by 91 gives me 3 as quotient and this is 3, this is what, 27, and this is 14, and 14 is remainder. Okay, so 91 into 3 plus 14. Alright, now say there is, these two number has some GCD, there is some divisor that is going to divide both of these numbers, there is some number that is going to divide both of this number. Okay, so any number that divides both of this number, let us talk about sum of this number. Okay, this is equal to this, so let us say m is a divisor of both these numbers, so m divides both of these numbers. Okay, so what do I know? If I divide this side by m and this side by m, of course I can do this, these two are equal, so I can divide both of the side by m, then this will be equal. Okay, now what do I know? This is equal to 91 by m into 3 plus 14 by m. Okay, and this is equal to 287 by m. Okay, now what do I know? M is a number. What is m? M divides both of them, right? So when I divide this by m, I will get an integer. Alright, when I divide 91 by m, m divides 287, m divides 91, I will get a integer. So integer into 3, still an integer. Alright, plus what do I know about this? 14, does it divide m or not? If 14 does not divide m, okay, what will happen? This will be a fraction. Okay, now an integer plus a fraction should give me a fraction. This will not be an integer, right? But I know this is an integer, so integer plus this must be an integer. Okay, so integer plus integer will give me an integer. I know this is an integer, I know this is an integer. If this is not an integer, then this equality will not hold, but I know this equality holds, so I know this must also be an integer. When will this be an integer? When m divides 14. So I am not talking about m being the GCD, I am talking about any division. Okay, anything that divides 287 and 91 must also divide 14. Alright, this is the explanation. If you did not understand, go back and watch again, but you should know this is very much intuitive. M divides this, m divides this. If m does not divide this, then we will have a problem, because it will be integer plus fraction. Integer plus fraction is a fraction, but we know this is an integer, so this must be an integer. Okay, so we know if m divides this and m divides this, if m divides 287 and m divides 91, that m should divide the remainder of, when we divide 287 by 91. Okay, so m should divide 14. Now one more thing, so let me write this down first, what I have observed. Okay, I have observed that anything that divides 287 and 91 divides 287 mod 91, that is the remainder that we get when we divide 287 by 91. This is 14. Okay, this is our observation 1. What is our observation 2? Anything that divides 14 and 91. Okay, 14, I know 287 is equal to 91 into 3 plus 14. Okay, now anything that divides 14 and 91 must also divide 287. Why? Let us say n divides 14 and 91. Okay, some n divides both 14 and 91. That means 91 can be written as some a into n into 3, plus 14 can be written as some b into n. Since n divides both 91 and 14, so a can be written as a into 91 can be written as a into n for some a, and 14 can be written as b into n for some b. Okay, so what do we know? If we take this n as common, we will get 3a plus b. Okay, so n divides both 91 and 14. This is how we can write 91 and 14. okay, where a and b, both of them will be integers. So 3a plus b will be an integer, okay, and 287 is equal to n into 3a plus b, okay. Now I can see that n is one of the factors, means of 287, okay. So one is the multiple of 287, that is 287 divided by n. I know this is an integer, okay, so 287 divided by n will be an integer, alright. So I know n divides 287 as well, alright. So what did I observe? I observe that anything that divides 91 and this remainder of 287 and 91, 287 mod 91, that is 14, divides 287, okay. This is my observation 2, okay. So I hope you understood both of this. I will not go into too much depth explaining this because this should be very obvious to you by now, okay. This is very school level arithmetic. So this is the two observations, okay. So what did we observe till now? We observed that anything that divides 287 and 91, okay, that is all the common divisors of 287 and 91 are also common divisors of 91 and 14, okay, and all the common divisors of 91 and 14 are common divisors of 287 and 91. That is anything that divides 87 and 91 also divides 91 and 14, and anything that divides 91 and 14 also divides 287 and 91. Some observation that we made. Now since anything that divides, all the common divisors of 287 and 91 are the common divisors of 91 and 14, okay, so the greatest common divisor of 287 and 91 should be equal to the greatest common divisor of 91 and 14. So if all the divisors are same, then the greatest common divisor must also be same, okay. So what do we know? We know that the GCD of 287 and 91 is equal to the GCD of 91 and 14, alright. So this is something we know by making these observations, okay. Now 91, if I divide by 14, I will see 91 is equal to 14 into 6 plus 7, I believe, okay. 14 into 6 is equal to what is 14 into 6? 14 into 6 is to 84, correct? 84 plus 7 is equal to 94, yeah. So 91 is equal to 14 into 6 plus 7, okay. Now anything that divides 91 and 14 must also divide 7, and anything that divides 7 and 14 must also divide 91. So the greatest common divisor of 91 and 14 must be equal to the greatest common divisor of 14 and 7, alright. I am not going to explain this again. We applied the exact same logic which we applied to come from here to here. The same logic when applied goes from here to here, okay. So GCD of this is equal to this. Now let us say 14 is equal to 2 into 7 plus 0, okay. There is no more remainder, okay. So what do we know? The greatest common divisor of these two number is equal to 7, so this is 7. So the GCD of 14 and 7 is 7, the GCD of 91 and 14 is 7, and the GCD of these two that we wanted to find out is equal to 7, okay. So this is how I know that the GCD of these two is equal to this. Now let me write this down as an algorithm. Okay, one more thing that I want you to observe is this. This number is bigger than this number, okay, bigger than or equal to. So we need this syntax. Why? Because GCD we called A of B. Okay. When we call the GCD next time, we had the GCD of B and A mod B. This equal to this. Okay. So this was the recursive call that we tried to make. Alright. So one more thing that I want you to notice, this will be less than this. Why? Say some number n when I divide by 5. Okay. So this is when A is divided by B, what is the remainder? That would be here, right? So when I divide something by 5, my remainder can be 0, 1, 2, 3, 4. It cannot be 5. After 4, my next number will have a remainder of 0. Alright. So when I divide something by when I divide something by B, the remainder that I get will be less than B. So B, this will be smaller. So this syntax of one larger than the smaller, this has to be consistent. Okay. This is larger or equal to this. This will be larger than this. The larger number is A, the smaller is B. Okay. We cannot swap this up in between. One time we cannot say this is bigger and this is smaller. Next time this will be bigger and this is smaller. We cannot swap that. Okay. So we have to be consistent. Why? Because somewhere in our program we will try to find this. Okay. AB. Say this is the signature. If this is the bigger number, this is the smaller number. Okay. So we will find bigger number divided by smaller number. We will find a remainder of that. Okay. So we are finding A mod B. If I give the smaller number here and bigger number here mistakenly, what will I have? I will try to find this smaller number mod bigger number. So that will be a mistake. Okay. Smaller number mod bigger number will give me the smaller number. Okay, that would be a mistake. So we cannot do that. So we have to be consistent when we write our program, that one will be smaller, one will be bigger. We have to make this rule that the first parameter will be bigger, second parameter will be smaller, or first parameter will be smaller, second will be bigger. Does not matter, but we have to make this rule, and then we will write our algorithm according to that rule. Okay, we will write our program according to that rule. Okay, now it is not difficult to implement this. Okay, so before calling this function, you can have a small condition check, so that first parameter is bigger, second parameter is smaller. If not, then swap these two number and then call. You can enforce this rule using your program itself. This is not a big issue. Okay. With that, whatever we did, let me write that down using algorithm syntax, algorithmic notation. Okay. So GCD of A and B, we are going to give x is equal to A, y is equal to B. Okay. Y is not equal to 0. What are we going to do? R is equal to B. A is bigger, right? X mod y. X is equal to y. Y is equal to R. We are going to do this until and unless y is not equal to 0. Once y is equal to 0, we are going to return y. This is our function. Okay. Here we have this restriction: A is greater than or equal to B. Okay. Let me call this using the two numbers that we had, 287 and 91. So GCD of 287 and 91. Here effectively this is not recursive call, but it is doing the same work of the recursion. Okay, so don't worry about that. Let us see how this program works to solve this call that we made. Okay, so here x is equal to 287, y is equal to 91. This is how we initialize. Then we go inside this loop. Inside this loop, r is equal to x mod y is equal to 14, x is equal to y is 91, and y is equal to r is 14, and we go back again. Is y equal to 0? No, y is equal to 14. So we go inside. While y is not equal to 0, what do we do? R equal to, what is x? 91. 91 divided by 14 is 7. Okay. Then x is equal to y 14 and y is equal to r 7. Okay. Now is y equal to 0? No, y is equal to 7. So we go inside again. R is equal to 7 divided by 14 equal to 0. 7 mod 14. When I divide 14 by 7, no, not 7 mod 14, 14 mod 7. When I divide 14 by 7, I get a remainder of 0. So R is equal to 0. X is equal to what? Y. Y is 7 and y is equal to R. R is 0. Okay. Now I go back again. Is y equal to 0? Y is equal to 0. So I come out of this loop. And what do I return? I return x. I do not return y. Okay. Alright. So I come out of this loop and I return x. What is x? X is 7. So I return 7. Okay. So what does my function return? My function returns 7. So 7 is the GCD of these two numbers. Okay, and we figured that out. 7 is the GCD of these two numbers. You can try to factorize this number and you will see that 7 is the greatest common divisor. Anyway, this is what we have. Alright. This is the GCD algorithm. Okay. This algorithm is known as the Euclidean algorithm. So this was invented by this philosopher mathematician called Euclid or something. Euclid, he's definitely not called Euclid. Okay, I don't know how to pronounce his name. There's Euclid or something like that. Anyway, this is what he invented. Okay, this algorithm. This is one of the first algorithmic approach towards solving mathematical problem. This is one of the first algorithm ever written. Alright. So the algorithm to find the GCD of two numbers. Very efficient algorithm compared to the prime factorization method. This is called the Euclidean algorithm. Alright. So I hope you understood this algorithm, how this algorithm works. Okay. Don't try to mug up the algorithm. Try to write the algorithm on your own. Try to remember what is happening, what is it that we are trying to do. Okay. So if you can remember that, if you can understand that, you can write the algorithm on your own. Okay, very simple algorithm, one of the first algorithm ever created. The last thing that we are going to do today is we are going to look at a theorem. This is called Lem's theorem. So it says let A and B be positive integers with A greater than or equal to B, then the number of divisions used by the Euclidean algorithm. Okay, this is the real spelling of Euclidean algorithm. If I made a mistake previously, this is the correct spelling. Okay, to find GCD of A and B is less than or equal to 5 times the number of decimal digits in B. So let A and B be positive integers with A greater than or equal to B, then the number of divisions used by the Euclidean algorithm to find GCD of A and B is less than or equal to 5 times the number of decimal digits in B. So yeah, this is what it says. We have two numbers A and B where A is greater than B. Now I want to find the GCD of A and B, okay, using this Euclidean algorithm. Now in Euclidean algorithm we have seen we are going to do a number of divisions. So we are going to do this division in order to find remainder, right? So we are going to find remainder at each step. So we are going to do a couple of divisions. Alright. So what is the number of division that we are going to do? According to Lem's theorem, the number of division is going to be less than or equal to 5 times the number of decimal digits in B. Okay. So if B has say k numbers, if B is k digits long, then the number of division required would be less than 5k. Okay. So yeah, that is what we have. So this is giving us a very good complexity on how much time this algorithm is going to take, right? So number of division required to find GCD is less than or equal to 5 times the number of decimal digits in B. So if B has k number of digits, so we are going to do 5k, at max 5k number of division. The number of division is going to be 5k or less than 5k, definitely not greater than 5k. That is what is given to us by Lem's theorem. Okay, so I hope you understood what this theorem is telling us. If not, read this again. This has nothing too much. Okay, very simple to understand. In the next class we will prove this theorem. Okay, we are not going to prove this theorem in this video. We will do that in the next video. In our next video, after proving this theorem, we will look at something called well ordering principle. So well ordering principle will allow us to do proofs like we did we have been doing in this video and the last video. Similar kind of proof we can also do with well ordering principle, and then we will see that this well ordering principle and this proof of induction, they are essentially the same thing. Okay, that also we will see. We will see that both of them implies one another. So that means both of them are logically equivalent. So all these things we will see in the next video. Today in this video we saw what is strong induction, and then we did several theorems using strong induction. Okay, including this Fibonacci number, this theorem about Fibonacci relation between Fibonacci number and golden ratio, and then regarding that every number greater than 2 has prime factorization, then every number means postage term worth rupees 12 and more can be made with postage term worth rupees 4 and 5. That also we had proven. Then we saw what is recursively defined function, and finally this Fibonacci thing that we did. So with this, and we saw Euclidean algorithm. Okay, and I hope you understood everything in this video, including this Euclidean algorithm. So understanding all this is very necessary. I hope you understood everything. If not, go back and watch the video again. And if you still don't understand, then please do feel free to contact me on WhatsApp, contact me on by mail, or call me, or write your doubt in the comment section below. I will be very pleased if you come up to me with doubts. Okay, don't have doubt, don't go on with doubts, right? So that is very important. Resolve your doubt. All right, thank you for watching this video. See you in the next video.